Hello, my name is Greg Troutwine, editor and associate publisher of Marine Technology Reporter magazine, the world's largest circulation publication serving the subsea sector. We welcome you here today to the OI Connect Navigation and Positioning track, where we will offer a trio of insightful presentations from organizations and individuals leading innovation in this space. First, we will hear from Gary Bago, Business Development Manager, IXBlue, presenting IXBlue Subsea Navigation Data Simulator and Performance Prediction. Next, Ludovic Bazin from SBG Systems will present how inertial post-processing in challenging survey areas is the way to go. Last, but certainly not least, is James Cowles from L3 Harris, who will present revolutionary autonomous subsea inspection capability, reducing ship time, increasing safety, and reducing costs. Without further ado, I would like to welcome Gary Bago, IXBlue.
Thank you much, Greg. Thank you for the introduction. Well, I hope you can see my screen. So a forward before on IXBlue. IXBlue is a high technology company. We deliver technologies like advanced autonomous, marine photonics. To illustrate that with numbers, we delivered more than 10,000 inertial navigation systems based on fiber optic gyroscope technology, with 80% for marine applications. That means we have a big expertise for the inertial sensor and also for the navigation algorithm. And today, when our clients come to us with more and more innovative autonomous solution, we can help them with this type of solution, a simulator, for the design of their vehicle, the selection of the navigation sensors, and also the mission planning. So we'll go through some slides to see that together. So about the why, the requirements for this solution. So when we speak about smart robotic and ocean exploration, we often think about long deployment. So you need to have robust system with a high level of robustness indeed. And also when they work on battery, we try to have long endurance with safe battery. That means to prefer alkaline to lithium. We have also to integrate our system within a lot of different vehicles. So we have to be able to communicate with other systems. So we have hundreds of protocols, and we are also compatible with ROS robotic middleware. Also, when it's about navigation, it's a lot of components, who are involved. So we speak about ecosystem. So our system needs to be agnostic, and they are agnostic to third-party sensor. And when it's about software, to manage this ecosystem from the simulation until the post-processing within the middle of the operation, we can also adapt our offer to the need. And finally, for the smart robotic and ocean exploration, it's very often about perception navigation. That means here we want to use a camera, a sonar, or more observation sensor to feed the inertial navigation system with, for example, position and speed observation made from the environment itself. So we have a focus here during this presentation about this simulation solution and how it works and what is the outcome for the user. So first of all, when it's about navigation strategy, the vehicle manufacturer or the vehicle user have to, in front of him, some mission objectives. Okay, so very often it's about the quality of the data that will be logged by the subsea vehicles and their georeferencing. So he will then to cover a survey area to define a vehicle trajectory. and he will select some navigation sensor to execute this mission on board this vehicle. Finally, he will go at sea to collect the data to execute the mission, and with post-processing, by performance analysis, he will finally confirm that he has matched the mission objectives. What we offer with the simulation is to reduce the need to go at sea to qualify a vehicle, to qualify a navigation solution, to qualify the good strategy to execute the mission. So how it works, inertial navigation, and what's happening inside an inertial navigation system? Well, you have inside the system what we call an inertial motion units, for example, with 3 fiber optic gyroscope and 3 accelerometers that will provide linear acceleration and rotation weights to the navigation algorithm. And also you can have some aiding sensor for position, for speed, for the depth, and the navigation algorithm that we develop is here to provide a navigation solution with a reliable confidence level. And as we said before, today, what you have to do is to go at sea to collect your navigation data, and then you can post-process the way that the navigation algorithm will process those informations to improve the quality of your data and to confirm that you have executed properly your mission. Here with the simulator, the good point is that you can stay at home, you can basically generate those sensor data without going at sea with a very high level of representativity if you compare that to a real mission. So the principle is that you will first define your vehicle. So you select what is the inertial navigation system on board. You select what will be the external sensors available and their frequencies. You will define the lever arm, the misalignment between the sensors. So basically, you end up with your vehicle navigation architecture. Now you can go to the trajectory. So what will be my survey pattern along my mission? So you will define a trajectory and we will generate navigation sensor data along this trajectory. So a trajectory is start at an initial position with angles and speed change. And once the user has declared this trajectory, we will add some information to have a more precise trajectory definition. And finally, we will generate some perfect data along this trajectory for the internal sensor of the IMU, the fiber optic gyroscope and the accelerometer, with all the compensation required. And also, we generate some external sensor, whether it is GNSS, USBL, or other aiding sensor. But that's not the end. Obviously, here it's perfect data. What we look at is a simulation result which is really representative to what will happen at sea. And all the sensors, they have some specificities and they have to be taken into consideration to have some result of simulation which are in line with what could happen at sea. So here we are going to add realistic errors. And just a small word about the type of errors. So we can mention the bias, scale factor, misalignment. They have some components. Some of them are constant. For example, when I have a DVL, so an acoustic speed sensor, if the vehicle is purely static, will my DVL tell me that I'm static? They have also some random components. So typically, an acoustic USBL system can have this type of white noise error components. And some of the errors are time correlated. So just to say that when we start from the perfect data generated over the specific trajectory, and we want to arrive to a simulated value, we will apply several, we'll perform several operations. So at each time, for each sensor, we will inject realistic error based on error models that we develop. And we find again here the different type of errors that we mentioned before. So that's how we achieve a simulation which is really representative of what will happen at sea. The benefits of that, it's obviously that I can perform my vehicle simulation, so the navigation sensor architecture on board my vehicle, the specific trajectory, and it's very important, the specific trajectory of my vehicle during my navigation, the availability of the heading sensor also during the navigation. Maybe I can have some loss of USBL sensor, some loss of DVL sensor. I will be able also to simulate the environment where is located my survey area. For example, if my AUV will navigate sometime in sparse LBL mode, I can upload in our simulator the bathymetry, the sound velocity profile to simulate what is the area insonified by this heading sensor. So here we also speak about the environment simulation. And finally, I will be able to see the accuracy of my navigation all along the mission. That means that I will know if the data that I will collect during my mission will have the proper level of accuracy when it's about georeferencing those data. So, well, to sum up, a simulation solution, it's about really upstream to select the good navigation sensor and also the heading sensors. It's about to converge faster with a good enough navigation strategy. And finally, when it's about developing a new vehicle, we can think, for example, about the resident vehicle, which are more and more coming for the energy industry. We will help to qualify the vehicles with limiting the seat reals. So it's basically helping the innovation by reducing the cost of qualification. Well, I think we arrive at the end of my presentation.
Okay, Gary, is that completed?
Yes.
Okay, well, Gary, thank you very much for your presentation. Next up, we have Ludovic Bazin from SPG Systems, who will present how inertial post-processing in challenging survey areas is the way to go.
Thank you, Greg. Thank you, Gary, for a previous presentation. So just let me present SPG Systems. We are an inertial manufacturer, so we are providing inertial solutions, mainly based on MEMS technology. And we have designed some miniature systems, and those systems are integrated quite often with some various sensors for survey purpose, especially into the marine industry for hydrographic survey. And we have some customers that are surveying in more and more challenging areas where we're going to see the positioning can be problematic even when we are on surface with some GNSS reception. So I'm going to present first how we reach high level of accuracy through post-processing. So most of the time, post-process kinematics can deliver an absolute centimeter precision using GNSS phase and range measurements by a double difference algorithm. To achieve that, you need to use a base station that can be either a single base that a user can have installed, or also some source of base station from cores. And the advantage also of post-processing is that you can perform an offline processing, meaning that you don't need any communication links while performing your survey. So the other advantage of post-processing is that you can have an absolute accuracy of your base station coordinates, because you can check and control them through some PPP static position. And also in post-processing, some of the post-processing software, you are able to perform some tight coupling, which is a specific positioning on processing method. So the ultimate performance with INS PPK also improves roll, pitch, and heading performance thanks to different methods. The first one, as I was saying before, is that you can perform a tight coupled GNSS INS solution, which means that we reprocess entirely a solution using the raw GNSS data on raw inertial data to improve the position. But there is also a forward, backward, and merge processing mechanism that will improve the accuracy, especially in area where you have some GNSS outages and in some rough area. So it improves position robustness in case of RTK or GNSS outage, and it's also greatly improved heading in mono antenna setups with MEMS systems. So one of the other advantages is that you can extend your RTK capability with post-processing. Thanks to different methods, either precision point positioning, which is commonly called PPP. You do not need any base station to perform a solution or to compute a solution with that. You can have some worldwide and free of charge corrections that can be available after your survey. But one of the backdrop of this correction is that you need a convergence time that is about 30 minutes to reach a centimeter accuracy. So you have to think when you are performing a survey to have at least 30 minutes of acquisition before being able to use the data set for survey. The other method also to extend those capabilities is to use a virtual base station concept, commonly called also VBS. This method consists in using multiple base stations around your survey area. And the advantage of this method is that you can have base station up to 100 kilometers from the area you are working. And we will modelize a map atmospheric disturbance at the rover location thanks to this network of base station. So you can reach RTK positions, centimeter precision, and having an RTK-like convergence time. So that's very efficient in that case. So this is an example on how we handle virtual base station in our post-processing software, Kinearcia. And the advantage of that is that it's ideal for long corridor mapping because you can use several base stations, so you can perform a survey on a long distance with being able to do only a single processing session. It's highly flexible and robust because you can mix some field base station that user can install, but also some base station provided from a local network or area network. And it works with all GNSS manufacturer. You can mix the GNSS manufacturer and the base position adjustment is automatically performed. So then the software will automatically find the best network for the area you're working, and using the base station and the data set that are available. It will automatically download the data, but also you have quite a lot of QC indicators. So we're going to focus now on a case study to show results you can obtain in real time and in post-processing. So what we did last year is we did a survey. We did some acquisition in Germany, in Port of Hamburg, with one of our partners, McCartney Germany. And we performed some acquisition in 3 different areas in Port of Hamburg. One area was open sky, so just to see the performance of the systems out there in a survey application in open sky area. And then we did a bridge survey. So we went under bridges and performed some acquisition using multi-beam echo sounders. And the last area we have been is our reverse channel through the Hamburg town, which is a quite challenging area. And this will be this area we will be focusing to show you the results. So the original objective of this acquisition was to show performance of our various inertial solution in multi-beam acquisition environments. So this is a brief description of the data set we used to perform this study. So we rigged the small vessels equipped with a multi-beam echo sounder, a CBAT 7125. We had for sure acquisition software to perform the record and the log of the multi-beam acquisition. And then we installed 4 different inertial sensors onto the boat, going from an entry-level systems up to a high-performance fog closed-loop system. So we installed an Ellipse D, an Equinox, an Apogee, and an Horizon. So for this study, what we have done, we have decided to compare the performance of all the sensors toward the reference sensor. That is here the Navsight Horizon, which is a closed-loop fog system. And we have used a post-process PPK solution of the Navsight Horizon as a reference for position. But then also, we have also computed and generated multi-beam data using each solution. And we have compared those multi-beam data to also this to the data set we have obtained with the fog and with the fog post-process solution. All the results are available and accessible on our website, on the SBG system website. But for this presentation, I will be presenting only this a specific data set. So as I was saying, we have been performing some acquisition into Hamburg channels that are called Speicherstadt, which is a very harsh environment for GNSS. So let's have a look at the results. So into this area, we had some tall buildings and also some bridges we had to pass under. And this is a quite challenging area for multipass effect. And we had some small outages going on the bridges, but the very big impact and the very big challenge into such area is a multipass effect. What is a multipass effect? If you look at this picture here, you can see all the yellow dots that are representing the position of the provided by GNSS receivers. So when we are performing acquisition, you have to rely for position, or you have to initialize at least for position on GNSS receiver. And then after we merge this GNSS receiver solution with the inertial INS data. The problem of the multipass effect is that the GNSS receiver tend to fix a solution and provide a quite good level of accuracy for the solution, even being offsite. This is part of the problem that you have when having multipass effect. And the inertial sensor, if we look at even the inertial track are still influenced into those environments by the GNSS solution. So if we look now at the data set and we look at what attitude and heading results we had in real time, so during the acquisition, and we compare them to the reference system, we can see that for the attitude, it's pretty consistent and there is not very big differences. So the pitch and roll can be used in real time. But if we start looking now at the heading, we start seeing that there are variation of headings into such area. One of the main points is that the system we are using in MEMS are based onto dual GNSS heading computation. And into dual GNSS heading computation, you have the same effect than for position. In multipath, you have some noisy data that are being computed because it's using the same mechanism of computation. And it impacts the results at the end of the heading that are not good enough for some accurate survey acquisition. If we look now at the position, at the result on the position, we can see that if we compare the position in real time to the reference system, and we add during the acquisition some RTK corrections that were broadcasted in real time, we can see that there are some quite big difference and quite big jumps into positions that makes the solution in position not usable at the end for the acquisition and to produce some proper multi-beam data set. So if we look now after a PPK solution, we look at the difference on the performance we are having for attitude, pitch roll, and heading. We can see that there is a visible improvement on heading, but also that there is a slight improvement onto the attitude, thanks to this processing forward, backward, and merge. It's really a way to achieve the highest level of performance you can have with any systems by performing the post-processing. If you look now at the position errors, you can see that from several meters of errors, we are down now to 30 centimeters for the Equinox, that is the mid-level sensor. And even for the Apogee now, we have everything below 10 centimeters. So we managed to reach a good level of accuracy by processing those, I mean, the data set, the inertial data set for almost all the systems. So it's really a very big improvement for position. This is thanks to the tight coupling post-processing method. That is very robust, especially when you have multipath, and then also thanks to the mechanism of computing a forward and backward solution that also improve the results at the end. So now what I'm going to show you is just the impact on the bathymetry itself, because for most of people on surveyors, at the end, they are not really looking at the performance of the inertial sensor itself, but really at what impact it will have onto your data set at the end. So we produce the bathy maps onto our website, and they are all available. And for each data set, you can have a look at the bathymetry itself, but also standard deviation and conformance, which correspond to some confidence level you can have on the bathymetry itself. So if we look, the data set I'm presenting here are the one from the Apogee, which is the higher grade MEMS sensor we can have so far. If we look at the bathymetry, we can see that we have some glitches in real time. And if we look at the standard deviation now, part of the standard deviation is above 15 centimeters, and we have part of the data that are not really usable to produce a bathy map or a survey map at the end. We can also see that on the conformance, which is the confidence level you can have onto your data acquisition, that you don't have a very good level of accuracy. If we look at the difference now of the bathymetry towards the reference system, we can see that we had more than 15 centimeters differences in some area, especially this area here. But in most of the area where we had bridges or even some other area where we had strong multipass effect, this happens. So if we look now at the bathymetry on the same area, but after post-processing the inertial data, we can see that we have a significant improvement on the standard deviation, but also on the confidence we can have onto the data set itself. The conformance start to be very good, and the difference to the reference system is almost is very small, and you can have a full usable data set that are perfect for such acquisition. So let's go back to the presentation now. So here we have an overall results performance summary of the different system. We can see that for both systems, the Equinox or the Apogee, in real time, the motion, pitch roll, and heading are providing acceptable results. But as soon as we go to the position, we start to the results are a bit too noisy and cannot be used as such for acquisition. So you really need to post-process the data, especially for the position, to reach a good level of accuracy, and that allows generating some multi-beam data conform to the IHO special order, and the performance of the IMU for sure is still noticeable, but the post-processing is really a very big improvement for that. So thank you. This is it for me. I think, Greg, you can take that again.
Okay, Ludovic, thank you very much for that presentation. Our anchorman today on the navigation and positioning track is James Cowles from L3 Harris, who will present revolutionary autonomous subsea inspection capability, reducing ship time, increasing safety, and reducing costs. James, welcome.
Good afternoon, and thank you for taking time to look at this presentation today. So today I'm going to be presenting on our ARISE program, which is the autonomous robotic subsea inspection for extreme environments. So it's a little bit different to some of the presentations that you've had already. But first, a little bit on who we are. So we're L3 Harris. We've been designing and building unmanned vehicles for about the last 20 years. And I think one of the key questions we want to ask at the beginning is, why are we using autonomy for subsea inspection? And that it's really key that we're going to reduce the cost. So with offshore wind taking off in the way it is, that's going to be a significant amount of inspection required of cables, of foundations and things like that. So it's really important that we can get the cost down to make offshore wind affordable. And with an increasing amount of offshore oil and gas installations going offline, the North Sea in the UK is decommissioning at a rapid rate. Decommissioning costs looking to ramp into the tens of billions of pounds over the next decade. It's important that we can reduce the cost of that as well, and also maintain our environment by being able to actually inspect with a cost-effective way some of these decommissioned sites on the seabed. And also in the times of COVID pandemics and remote working, how can we mitigate the challenges of vessel and crew availability? As people can't get offshore, less vessels can go out and do work. So how can we mitigate that with the use of autonomous technologies? So as I say, we've been developing these systems for a number of years, and have an industry-leading autonomy system capable of doing a wide range of things. We're constantly innovating, and that is from just the simple autonomy of remote operations all the way up to advanced autonomy. So you can see in the video here a vessel tracking using camera systems. And then what I'm going to talk to you about today, the Arise system is on the phase 1 is on the screen now. So how do we integrate an ROV into an existing platform and then go and use that to do useful inspection work? And we developed a whole range of different vehicles from 3 all the way up to 13 meters, and in both the military and commercial world. So mine countermeasures, border security, as well as hydrography and survey. So to talk a little bit more specifically about what we've been doing. So this is a 2-phase program. And the first phase, we did a relatively simple integration, shall we say, where we took a lot of equipment that we had around a simple winch system, a payload in an existing vessel, and integrated that with about 40 meters of tether to enable us to just go out and prove the concept. How can we, in as simple a way as possible, integrate an ROV into an autonomous vessel so that we can start moving towards this collaborative autonomy? Because at the moment, we're looking at sort of an ROV that's around the size of a Saab CI Falcon. That's what we've used in the original phase 1 of the program, and what we're going to be using to do demonstrations early next year. And that's going to be traditionally operated off a vessel that's anywhere between 25 to 35 meters long. So it's going from that size down to 7 meters is a significant step. And if you look at things like carbon emissions, you're reducing them by up to 97% by making that step. This system can be using as little as a couple of liters of diesel an hour, which is vastly different to a lot of sort of crew transfer vessels that are using these ROVs for inspection work at the moment. So, as I say, a relatively simple system, quite a small winch on top of this system, obviously a USBL system so that we could position the ROV underneath the vessel. And then we used just the off-the-shelf ROV control system to integrate into our system and then control it over our standard comms link. So this was some trials we did in 2019. And it was extremely successful. We did a number of dives down to about 20 meters in total. And what we did demonstrate was a progressing level of autonomy. So what we were looking at was, okay, do we have to actually have 2 people controlling these systems at all times, or can we actually now start stepping towards the future, which is where we want to be able to give missions to the system and it can go off and deliver them? Actually, what we found with very, very limited intervention in our standard systems, we could use our follow target behavior to follow the ROV. We hadn't got an ROV in-house yet that has any line following capabilities, but that could easily follow it. So we were able to follow the ROV, much reducing the load on the operators. So it was a really successful thing. One thing we did learn is that we developed our follow target behaviors for use with AUVs. AUVs being very good at going in straight lines, and our target follow behavior being very good at following things in straight lines. When you're using it on ROV, it does get slightly confused when the ROV goes sideways. So that was a lesson learned off phase 1 that we're taking on and trying to develop a bit further. So with this platform, as I say, we're getting really good fuel economy. So the vessel would be able to go out and do extended duration missions. So going out into, say, the middle of the North Sea and deploying the ROV, doing 10 days of inspection and returning is a really feasible operation. In the first phase of the operation, we weren't doing sea states, so only up to about sea state 2 was our deployment, but still very successful in the simple system that we had, where you can see in the diagram in the bottom right hand corner, it's only going up into a simple garage system there, so it's not got much wiggle room. So it was a really interesting challenge for the pilots. So the control system, relatively simple. So we had a desktop here for the winch control, hand controller for the ROV, remote desktop into the ROV system, so giving camera feedback, details on thrusters, more cameras, because the critical thing we found was actually controlling that tether and making sure that we weren't getting any wraps on the winch or anything like that. And then finally, our control system in the background there, giving that overview of charts and where we are in the world at that time. So, as I say, a relatively simple system which could be mobilized quite easily, even in this kind of prototype format. But as I say, this was a prototype, and we only had about 40 meters of tether on board. So this is what the system was looking like. This is the wonderful trials area that is the Solent. So whilst good for us to trial the launch and recovery, deploying the ROV repeatedly to ensure it was operating appropriately, it was terrible for doing any actual demonstrations of inspection because the water is a bit like mud. So we moved down to Plymouth to give it a trial, and also worked with an organization called Abyssal to do some visualization with the project partners BP, so they could actually visualize what was going on in their head office. Actually in Plymouth, in Corsan Bay here, the water was much clearer, so we can even see the ROV coming out of the housing underneath the vessel, just behind the USBL system there. And then we got some beautiful imagery of sandy mud. And if you looked really careful, there was a small crab there, but that's about all we saw, unfortunately. Did a bit of inspections of quaysides whilst we were getting ready, but really just get the system out there, demonstrate capability, and enable us to move on to the phase 2 program that we're operating now. And really the phase 2 program is very much around hardening this system and taking it to the next level. Our goal was always to get to around 250 meters of tether, enabling us to operate down to about 200 meters water depth. And the reason behind this is that would enable us to access about 80% of the North Sea. And with access to 80% of the North Sea, this suddenly becomes a really useful tool. Offshore wind, obviously most of that in the UK, or 99% of it in the UK, is less than 60 meters water depth. So that would be able to access all of that. And also the vast majority of oil and gas projects would be within that as well. So a really successful project. You can see the Abyssal system here, which was doing real-time observations. So what we did with this is simulated some oil and gas infrastructure on the seabed and trialed the inspection of that. So that enabled us to move on to the second phase of the project. And in the second phase of the project, we were going to design and build the ROV LAR system, working with the University of Exeter, who are going to model the ROV and ASV interactions to ensure we're not going to get any loads that are too high on that tether, and how we're going to recover that system into the ASV. And then we were also supported by BP as industry partners. This was a follow-on project with the Innovate UK, so they're providing a lot of government funding to this, so it was brilliant. And as I say, the goals for Arise 2 were significantly higher than Arise 1, so we were going for over 150 meters of tether. Goal was 250, but it just wasn't practical in the space that we had. We're also looking at a significantly larger ROV if possible. For trial reasons, we are going to stick with a Falcon, but it is capable of taking something up to about the size of a Tiger and some other systems that are out there. And also the ability to provide much more power. One of the challenges we know that we're going to face in the commercial environment is the speed of the tide and ensuring, certainly in shallow waters, that we can stem that tide and actually complete our inspection work. And that's why a more powerful ROV system is really extremely useful. And then the core challenge that we're also looking at in this program is operating this over the horizon. We've been operating vessels over the horizon for about the last 5 years, but it's very different operating just a single vessel, which is on the surface all the time, to two combined autonomous systems, that one below the surface and one on the surface, that are then actually linked by a tether. So how do we look at that autonomy? And that's a bit of the work that's sort of kicking off at the moment. And also importantly is the operational sea state. The prototype system did achieve a better sea state than actually we'd imagined it would, but realistically, places like the North Sea, we need to be achieving sea states for operational, or else our operational window is going to be so small it's not going to be worth looking at. So where are we? That is a picture of the winch system in our factory now. So it's being commissioned as we speak. The tether, a test tether has been loaded onto the system, and we are trialing the use of that at the moment. It's going to be able to fit 175 meters of tether. It's a hydraulically powered winch with a powered sheath to ensure that we can wind the tether on neatly onto that winch. And the rest of the components of the system are actually brought across largely from the previous system. One of the challenges this did create for us is that in the original Mark 1 system and in most of our 7-meter boat payloads, we have a rack system that sits in this section. But as you can see here, that's currently filled by a large winch. So we had to find an alternative location to store, excuse me, the electronics. Now, luckily, we had a bit of space in the bow and in the stern of the vessel. So in the bow of the vessel, we fitting a 12U rack system with air conditioning so that we can take all of the ROV top sides in there. And in the stern of the vessel, we're going to fit a set of inverters to be able to give us the 3-phase 15 kilowatt power. So we've actually made significant progress with this. Unfortunately, due to where we are with the pandemic and trials, it's taking longer than we'd hoped, but we will be out early next year gathering data and trials in real world environments. So going back to where we started, why are we doing this? By reducing man days offshore, we can increase health and safety, even especially in the current pandemic times, we can mitigate some of the challenges that's creating. By moving from what would traditionally be a 35 to 40 meter vessel doing this work to a 7-meter, we can significantly reduce both the capital and operational costs. And then a much lower environmental footprint, 2.5, maybe 3.5 liters an hour during operations. It's a significant improvement on where we were. And also we are working off a base vehicle that is a really high TRL. This system has operated around the world and is extremely robust. So we know that we're building on a strong technological footprint. So where does the future lie with this project? Well, early next year, we will be trying this in shallow water inspection applications. Down to about 70 meters is the goal for both integrity inspections and environmental inspections. And then we're also looking at what the future holds in terms of larger ROVs for bigger scopes of work. So can we do the work of, say, a 70 or 80 meter ship with something like a 24 meter ship? So really looking to the efficiencies of this and how autonomous systems can support operations in a more cost-effective way than we look at it at the moment. So thank you very much for listening to me, and I look forward to any questions. Thank you.
Okay, well, thank you, James, Ludovic, and Gary, each and every one of you for your presentations. As you know, we don't have a live audience, but I look forward to a conversation with all of you. I have a first question, and this is to all the panelists. From each of your perspectives, and again, 3 very different presentations, but from each of your perspectives, what do you consider to be the biggest market force today that is driving innovation in your respective companies, in your respective sectors? And simply put, who are your customers? What are they asking you to do?
So maybe I can start if you want, Greg. To us, what we see from our clients is a request for a navigation system that can provide a good level of robustness for autonomous mission, which are going to be longer and longer. So robustness accuracy, and also when it's about subsea drones like AUV, like smart ROV, it's also not only a question of accuracy, but how will be fuse the data to maintain the accuracy, whatever the mission will be. It's also obviously about power consumption of the system in an autonomous vehicle, and something which is pushing us to reduce always the system with the same level of accuracy and with low power consumption.
Excellent. Thank you, Gary.
Yeah, I can continue on my side. I think I'm going to be a little bit on the same aspects than Gary, but we are more or less onto the same business, but with different method, with different technology. But that's the same. What is really driving us now is really the miniaturization of the systems, because we have more and more customers asking us to integrate that in some autonomous vehicle, but that tends to be smaller and smaller. And also to have low power consumption, and probably fuse different type of aiding sensor, what we call aiding sensor, external sensors, to reach a good level of accuracy. So yeah, that's really the autonomous market, or the autonomous vehicle market, and probably also miniaturization of the system is something really driving us.
I guess to sort of follow up on the theme of the autonomous market, yeah, what I think why customers are going to autonomy now is cost is really a key driver, and just the sheer amount of inspection work and survey work there is out there in the world. We've still only mapped about 20% of our oceans to any significant detail. There's no practical way of doing that with traditional technologies. You've got Australia at the moment trying to map their EEZ. That is a phenomenal amount of work for that country. So there's no way you could do that with traditional vessels. You need to be using autonomy, and it's not, whilst it's lower cost, it's lower cost per mile, not reducing the amount of money you spend. It's about getting more for your money, and also more for your people. A lot of survey organizations will spend a lot of money training people straight out of university to become great surveyors, and they'll go out to sea, they'll spend 10 years at sea, and they'll become party chiefs, and they'll go, oh, this is great, I'm enjoying this, but now I want to go and have kids, I want to go ashore, I want to be with my family. And that's a really major challenge. But actually, through the use of autonomy, we can support those people further into their careers, and providing that expertise to people coming fresh out of university, working more in an office style environment. So it's keeping skills in the industry as opposed to them coming ashore and doing different things. So I think it's a really positive thing on a number of cases, and solving a number of issues that customers are having at the moment.
That's interesting. Thanks, James. And again, I remember seeing your system. We were in Southampton, I think it was 2 years ago, at the Ocean Business, and we were standing and watching the system and doing a video interview. Now, you mentioned specifically the offshore wind sector, and obviously, when I look at the technology, I see a multitude of potential applications. Offshore wind is one, but if you had to project, just coming out of the box, what do you see the best opportunities for a quick uptake on the technology that you're working on at L3 Harris?
I think at the moment, offshore wind really is an absolutely monster market. They are, in the UK at the moment, we are building offshore wind crew transfer vessels as quickly as we can build them. And I know it's kicking off in the US as well now. So to be able, at the moment, what happens is they go, okay, we've got to do an inspection campaign. Let's get an ROV. We're going to go and bolt it to the back of a crew transfer vessel that's got massive engines designed for going fast between wind farms. Oh, and we're going to make it tootle around really slowly. It's massively inefficient. So yeah, to be able to increase the efficiency of the operation, I think is the nearest term market with sensible environmental conditions, because the offshore oil and gas market that we're looking at the moment is also got significant challenges around operational conditions. Like that, it's an achievable challenge, but it's one of the reasons we're looking at a larger vessel at the moment. So yeah, I think really offshore wind is the key market here, but that is kind of alongside some of our historic stuff, which is around just traditional hydrographic survey. We've been doing that for a half a decade now, very successfully. Thousands of miles around the world have been done with our vessels. So yeah, but that is very dependent on places like, I don't know, Australia, US and UK, who are doing large seabed mapping programs. So yeah, it's a interesting time, but yeah, a lot of growth to be had.
Trust me, we're watching the potential growth of offshore wind in the States very quickly. I live in New York, so
Yeah,
we're pushing for that as well. Hopefully, it'll finally come to fruition. I have another question for all the panelists, and if you prefer, we can just go in the order in which you spoke, so everyone can know their place. But obviously, in all of your businesses, faster, better data, cheaper, smaller, is a driving force. But when you look at your technology in the sector as a whole, what do you consider to be the greatest hurdle ahead, and how are your companies investing to get over those hurdles?
So there is a first point which comes to my mind. It's what about you are going to present an autonomous vessel like James did, or a autonomous subsea inspection solution to a client. There is always in front of you somebody in the room who said, and what if this failure, what if that happened? So there is a change in paradigm. Now there is more and more autonomous solution, more and more drones. People are attracted to this solution because of cost reduction, risk exposure limitation, and carbon footprint, and so on. But there is always, a scale of the people to see autonomous drones with more or less human in the loop to approach a structure in production, like a wind turbine pile, like a wellhead for oil production. And so that's why we presented today this inertial simulation solution, is to be able to prepare the mission, demonstrate whatever the condition, whatever the heading sensor available, we can predict the behavior of the navigation solution on board a surface drone or a subsea AUV.
Excellent, thank you.
Yeah, I think, this is true. The reliability of the solution that you have to provide is really increasing, and the technology also is moving very fast now. I mean, most of sensors that can be installed, or a solution that can be provided for autonomous vehicle, especially, but then also any vehicle that have to approach some structures, that have to go into in town. I mean, even if you look at the market that you can have on land with the autonomous cars and so on, they have to go in some locations. They have to be very reliable, and at the same time, let's say, they have to be autonomous for a long period of time. So there's really a kind of a combination of a technology that is moving pretty fast, but that also is on the customer. You have a high demands, let's say, in terms of reliability, accuracy, and so on. So you really have to go very fast and be very reactive in developing some solution, improving our solutions, even the hardware, the software, firmware, etc. So this is probably one of the big hurdles that we have to do, and we have to put a lot of R&D effort on our side, and this is the way we have decided to go. It's really focus on R&D, on developments, and looking at the new products, looking at the new solution, pushing everything as far as possible. So I think this is probably some high demands, but on one side, this is very challenging and pushing developments. So yeah.
Thank you.
Yeah, I think sort of just building on what Gary and Ludwig said there, it's not only the customers that actually create the challenge here. The customers want data and they want assurance that there's low risk, but ultimately the people who have, I don't know, less to gain from this, but have put the ultimate blocker in the way are the regulators. there is challenges around the world about how we get autonomous vehicles accepted by regulators. And we're looking at the IMO and people like that who are working on it and are being really supportive, but it's a long and slow road. And how do we demonstrate in the meantime a level of equivalency to manned traditional standards so that we can continue to operate and grow? So I think that is a major challenge, but it's also one that's kind of coming along. And also I think what is helping is places that are doing larger programs of autonomy. Norway is doing a fantastic job at the moment to push this technology forward, and it's going to draw all the regulators together. In the UK, the MCA have just finished a program called the MARLab for working out how they're going to integrate autonomous systems into UK regulations. So I think it is a challenge, but it's one obviously we've been working on for a number of years, working very closely with the MCA in the UK and the IMO, and also the Maritime Autonomous Systems Regulatory Working Group. So yeah, it's a big challenge, but I think it's one that we're going to solve in the coming years. And also importantly, in the meantime, we've got ways of working with the regulators to do a case-by-case basis.
Excellent. Thank you, James. Ludovic, I had one specifically for you. In everything that we do in our maritime, our subsea, our port, our logistics, our offshore energy business, much talk today comes down to data and information, and taking that data from its raw collected to the finished product, where it can actually provide actionable intelligence. Can you discuss a bit the effort, the time that post-processing can require?
Yeah, that's always a question especially when we are discussing with surveyors and speaking about post-processing some data. They're always saying, okay, but what's going to take? Because the old memories, people from the old time were saying, okay, 1 hour of acquisition is 1 hour of post-processing. So if I can spend, if I don't have to spend this extra time, that's going to be much easier. But with all the modern software now, and also the power of the machine that you have, the power of the computer that you can have, to be honest, post-processing can be very fast. In inertial, on our system, the inertial post-processing software, if I take, I don't know, a 3 hours data set, for example, it's going to take not more than 5 minutes to do the processing for it. So that's not a huge effort at the end to improve your data set. So yeah, this has really changed since few years. So now it's very fast, I think, for post-processing. After, it depends on what you're looking for, on level of accuracy you're looking for.
Okay. Does the post-processing apply only to the inertial MEMS-based systems?
No. It applies to all the systems. On the presentation I did not show all the data, each sensor. But if you look at all the data, you will see that even the closed loop system in some, so for closed loop system that in some area has to be post-processed also. As I was saying in the presentation, some area, especially when you have multipass effect on the GNSS, there's no inertial system that can really get rid of this effect, because at the end, the GNSS is telling you, okay, I'm here with a good accuracy, but in fact, it's outside. So you have to do post-processing in that case to recover that.
Excellent. James, actually, I had one specifically for you as well. I know that you're just starting the phase 2 portion of your program. I know that the situation is not currently normal with the ability to conduct it. And I don't want to put your feet to the fire for all of L3Harris in telling me when you're going to bring this system to market. But if you look at the progress of your system today, realistically, when would you project that the types of solution that you're working on and propose would be something that would be on the market, ready to roll?
I think the goal is it'll be on the market for further discussion, shall we say, next year. The goal is for it to be in commercial operation next year, but rollout of kind of purchase systems might be move into 2022. So it's not a million miles away. It's not. I think that one of the core things is we focus very much in this part of the phase of the program on the mechanics and the electrics of it, because once we've got those robust, to enhance the software side of it in the background, it is quite simple. So we can enable customers to kind of enhance their capabilities throughout time with additional software upgrades.
Okay, thank you, James. I just had actually one more question, and it's the COVID-19 elephant in the room, as you might say. I had originally targeted for James, but I really want to throw this open to everyone if you choose to answer it. It has been argued that the current COVID-19 pandemic and all that it entails will effectively fast track digitalization and some of the highly automated solutions that all of you gentlemen have discussed by years, if not a generation. In fact, in a recent edition of Marine Technology Reporter, we interviewed Rear Admiral Tim Gallaudet of NOAA, and he specifically was talking about some of the challenges that NOAA was facing and how they were able to jump over these challenges with autonomous systems, specifically in regards to fisheries monitoring. So when you look at COVID-19 and the situation that we face today, the technology that you all provide, how do you see this current market impacting your technologies in the long run?
Well, it's an interesting question. You mentioned the NOAA. Actually, we exchange also a lot with them. They are using our surface drone, the DRIX, for their hydrographic operation. But I would say, in general, we knew that for autonomous system, for drones, risk exposure, cost reduction, carbon footprint would be three main vectors. But COVID-19 has also bring a new issue is the crew transfer, the logistic for the rotation, and this is indeed adding a new stimulator to this transition to autonomous solution for any application, scientific, but also in the energy industry.
Thank you.
Yeah, I think on our side here we can see that there is an increase of demand, especially for all the autonomous vehicles, and it can be any unmanned solution, let's say, that can be on land. On our side, we are not only onto the marine industry, we are really on any kind of industry, also land and air industry and so on. So yes, the unmanned solution is really something that is being pushed so far. But I mean, for the moment, that's still quite hard to understand exactly what will be the exact impact, because we know, and this is the same for us, that a lot of companies are because of the current situation, COVID situation, are putting a lot of R&D efforts. But at the end, we need also to see what will be the exact impact. And as soon as things will start again, maybe more normally, if all those R&D efforts will be continued. But yeah, really the unmanned solution is something everybody is pushing.
I think it will have a slightly positive effect, but I don't think it's going to be many years of kind of acceleration. It'll just bring it forward a bit. And that's broadly because autonomous systems have been coming to the forefront of certainly the marine world for quite a while. The developments over the last 4 or 5 years really have been kind of substantial, from there being, just look at the number of players in the industry and how they've multiplied over the last 2 years, and how certainly the systems we're providing have gone from prototypes to systems that have been out for thousands and thousands of kilometers and go out repeatedly for days on end. I think that really shows that the systems are becoming mature and the customers have been pushing that maturity. So I think, yes, it will stimulate a lot of companies that weren't necessarily pushing it previously to start looking there, but ultimately it's been a wave that's been coming anyway. So yeah.
Excellent. Well, gentlemen, that's all I have for you. This has been an innovative and interesting way for Oceanology to celebrate its 50th anniversary. And hats off to the organizers at READ for trying to pull together all the experts from around the world. I'm sure you would prefer to have your clients sitting, watching, and doing a deeper dive, but I'm quite certain that everyone knows your companies or you personally. They know where to find you, and I look forward to continuing the conversation in the future in person.
Thank you.
Thank you.
Thank you.
Okay.